Hecke's theorem and about conversion for three manifolds. But first, I'll just recall some of the basic notions, even though they already appeared before during our dance talk. So I'll talk about the difference of an extension of number fields. So I'll denote by OK the ring of integers of a number field. I'm taking some extension, and I want to talk about the difference of this extension. So first, let me define the codifferent, which is going to be the fullness of the difference. To be this fractional ideal of all the elements, such that if you multiply them by an integer, the trace is going to be an algebraic integer. You can easily check it's a fractional ideal and take the inverse of that to be the difference of the extension. And you check that the difference is an integral ideal, so it's an honest ideal of the ring of integers of the bigger field E, basically because the element 1 is contained in the codifferent. So why are we interested in this invariant? Why are we interested in the different and the codifferent? I'm going to give a few reasons or a few equivalent definitions for one to motivate why should one care about this invariant. So first, if you care about the discriminant, it's reassuring to know that this is a related invariant, and you can redefine the discriminant in terms of the norm of the different, or you can define the discriminant as the sort of volume of a certain lattice, and then take this as a property, a proposition. Another way to define the different is in terms of
You're thinking discriminant as an ideal of OF, or it's just or no?
Yeah, I'm taking For me, the discriminant is going to be an integral ideal. So you're right that sometimes you can, for a lot of what we're going to discuss here, just take F to be Q, and then this the discriminant ideal is going to be principal. If you're more comfortable with F equals Q, you're not going to lose. So there's also another way to describe the different as the Kähler differential, in terms of the Kähler differentials of the extension of OE over F, and that's done as follows. You look at the multiplication map, and you take all the elements mapped to 0. It turns out that this is an ideal, and also a module for, can I do the pointer? Oh yeah, for OE, and you include OE into, say, the left part, and then you do 1 on the other tensor factor, and inclusion gives you a structure of an OE module, and then I square the square of this ideal inside this algebra is also an OE module. The quotient of this is also an OE module, and the annihilator of that is another equivalent definition for the difference of an extension. Yet another equivalent definition is that the ideal is generated by taking all the generators of the field E over F, taking the minimal polynomial, computing the derivative, and then plugging this into the derivative. You obtain a bunch of elements, and these elements generate the different ideal. And so this is a special case of something that Artem mentioned in his talk, that if the ring of integers is monogenic, if it's generated by one element, then this ideal is you can just take alpha to be that generator, and that already gives you the whole ideal, but that's slightly more general. And there is also a further equivalent way to define the different, and that's in terms of its prime factorization to prime ideals. So it turns out that every prime P, the power in which it will appear in the different, the number of times it will define the different, is at least the ramification index minus 1. So this ramification index is 1 for almost all primes, so it's, you see, is of course only divisible by finitely many primes. And you can moreover show that this is equal to EP minus 1, that this inequality is an equality if and only if this prime is tamely ramified. And I'm emphasizing the tamely ramified case because that's what's going to be most relevant case for the analogy with three manifolds in a moment. But you can generalize this inequality to an equality in complete generality in terms of the ramification groups and the ramification filtration of the local Galois group, of the decomposition. It ends up being a formula which is a little messier than that, but still you can say what's the precise multiplicity of every prime in the different, and that's of course also pins down the different unique. Okay, so that's a sufficient amount of different definitions and properties. Yeah, question.
Yeah, so you have to go to the rest of the ramification filtration or just
Yeah, I was saying that you can give a formula here, which is not an inequality, which is an actual equality. Oh, sorry. And this formula involves the ramification filtration at this prime P. For example, it's I think in Sayre's book, Local Fields.
okay, yeah, okay, so you don't have that. Okay.
All right, so now I want, once we have some familiarity with the different, I want to say what Hecke's theorem is, and maybe say something about the proof of this theorem. So Hecke shows that this different ideal, at least when we look at it in the class group as a class, is a square of something else, is a square of some other ideal. More explicitly, it's a square of some other ideal up to principal ideals. That's what it means that it's a square in the class. Yeah, this if you recall that when we take norms, it also means that the discriminant is going to be a square, but that's a more basic fact, which I think was proven by Steinitz, or maybe even earlier that was not. So that's a refinement of something which is simpler to prove for the discriminant. So we will restate this theorem in a few ways, which will both help us prove that this theorem and also will be helpful later when we talk about the analog for three manifolds. So of course, saying that something is a square in an abelian group is like saying that it's trivial when you pass to the maximal elementary abelian two quotient. And here is another equivalent way to say this. If you take any quadratic character of the class group, or of the class group when you tensor by Z mod 2Z, it doesn't matter because it's the same characters. Then when you apply this character to the different, you get 1. So that's also another characterization, or squares in any finite abelian group. Yeah, so this already suggested that the proofs that we're going to see are not going to exhibit any specific J, which is what Artin called spin structure, but rather just showing that it's a square in some way without picking the square root, some roundabout way. So in the proof I'm going to sketch next, I will assume for simplicity that the base field is Q, because just that notationally it's a little simpler. And I also recall another property of the different here is that the different is purely local, and that's something I was alluding to in this formula with the ramification groups. In particular, one consequence, you can also prove it in a different way, that the multiplicity of any prime in the different is something you can read off from completing in this prime. You can also define the different of an extension of local fields, or basically of any extension of Dedekind domains. We can sort of from the local information piece it together and get what the different is globally by this product over primes form. All right, so now we will go into the proof of Hecke's theorem. It's not Hecke's proof, it's a more modern proof, but somehow what Hecke did is sort of still there secretly. The modern way to think about this character of the class group is to lift it to a Drosen character or Hecke character, namely a character of the Udels. And then we try to apply this character to the different, but then because everything here admits a product of formula, a product of local terms, namely both the character and the different, we can split this value that we want to show that it's one product of in this way of the local difference and the local pieces of the character. And then what the most somehow one of the significant steps is hidden in this simple equality. What you see on the right hand side, this epsilon is something called the epsilon factor. Sometimes it's also denoted by W in certain sort of books. And this is a factor that appears in the functional equation of the L function of these characters chi and chi v. So the functional equation is a certain symmetry between s and 1 minus s. And it's not a perfect symmetry. There's a certain extra factor that appears there. And this is sometimes called the epsilon factor. And this epsilon factor, you can give an explicit formula for it in terms of Gauss sums. If you have worked with L functions of Dirichlet characters over rationals, you have seen that in the functional equation there is something related to the Gauss sum. And so when you evaluate this Gauss sum, because the characters chi v are unramified, so they lifted them from the class group, so it means that they're unramified characters. You can evaluate this Gauss sum in a reasonably simple way and see that it's related to the different via this equality. So this is really an equality that happens for every v separate. For every v, this Gauss sum, something which is secretly a Gauss sum, evaluates to this chi v of the different.
So that equality holds after taking product of all v, or
Both after and before.
both?
Yeah. Yeah, so it's true for every v separate. Yeah. And now we go global. So the go global again, I would say. And so one of the things we learned that the epsilon factors, when you multiply them up, you get the epsilon factor of the original character pi. And now somehow the last step is also by modern standards pretty simple, is that if you work with a quadratic character, the epsilon factor is always going to be 1. So if you look at the functional equation of the quadratic character, there's not going to be a -1 sign there ever. It's always going to be +1. This is something that, for example, is proven very nicely in Tate's thesis. But of course, you can prove this also much more elementary. All right, so maybe I should mention certain generalizations of Hecke's theorem along the lines that Artine mentioned in his talk, related to Deligne's work and to Stiefel-Whitney classes. What Deligne has shown, the way he generalized this, is instead of a quadratic character, if I remember correctly, he took a symplectic representation of arbitrary dimension, finite dimension. So finite dimensional representation.
It's orthogonal.
Again.
Orthogonal representation.
Orthogonal, not symplectic.
Not symplectic.
Okay, orthogonal. So the paper talked about both that and symplectic. So for symplectic, the result must have been different. But yeah, thanks a lot for correcting me. So an orthogonal representation. And also, okay, yeah, of the absolute Galois group of the number field, or of a function field for that matter, and proves that in this case the epsilon factor has to be equal to 1. Oh, now I guess I want to say something about the analog of that theorem for 3 manifolds. So let's just build up the analogy. So we have a degree n cover. So n here is just the letter which I use to denote the degree. I'm assuming the manifolds are closed, but not necessarily orientable. And I'm assuming that this is a branched cover, so it's branched over a certain link. So this is, I'll use some notation. So L is the link in M, this is the branch locus in M, and L tilde is the branch locus in M tilde. So that's my analogy for the extension of number fields. And these L and L tilde are sort of the product or the union of all the ramified primes, the extensions. So the class group for me here is going to be analogous to the first homology group. Maybe one reason for this analogy is because the class group is Booleanized the tall fundamental group, and H1 is also the Booleanization of a fundamental group by Hurewicz theorem. And so if you remember, so from the previous slide, I eventually want to work with the class group tensor with Z mod 2Z and show that some class is trivial, and I'm using universal coefficient theorem to show that to show that I can just also view it as a homology. Yeah, now I realize that symplectic vector spaces are two-dimensional, and therefore I should have figured out that the character, which is one-dimensional, should have not been symplectic. Yeah, that was a good sanity check. Okay, so now let's talk about the analog of the different in this situation, or more precisely, the analog of the class of the different in the class group mod 2. And the analog I want to take is basically coming from the characterization of the usual different in terms of the multiplicities of the primes that divide it. So in the tamely ramified case, we saw that the multiplicity is always the ramification index -1. And that's basically what I'm using as my now definition for the different, or for its image in the class group mod 2, or precisely in the first homology group with coefficients in Z mod 2Z. So this is a very somehow we're very lucky that we're able to to write it this way, because if we would use some other coefficients, for that to make perfect sense, we would have to orient the knots inside the link, or orient the link, and that's not maybe not desirable, because perhaps there isn't a canonical way to do this. So in some sense, we are lucky that we work with Z mod 2Z coefficients. Question, David, yeah.
You really have to be in dimension 3 in order to get something in H1. I guess.
Well, it's possible to try to think of generalizations also in higher dimensions.
You add like, so let's say 5 manifolds, for example.
Right, but if you, yeah, so the question is what the ramification, what is a
Branch
branch
locus.
covering for 5 manifolds? And I think is different people here could have different opinions of what would be a natural definition.
It's
I'm
not
not
manifold, it's the branch locus, right?
right, but a branch covering here is more than just saying that the branch locus is a link. So you need to have this well-defined unification indices. So like locally, it should be like a rotation, but like raising to the power e, basically.
So you're assuming tamely ramified primes when you do this analogy?
Yeah, because I don't know how in the setting of three manifolds in this analogy, what would incorporate wild ramification from the arithmetic situation. So that's sort of my best guess for like what.
Wild ramification in the let's say, if there is some sort of like net field analog of this.
Yeah, so there's a function field analog of this, and that's the analog there is just like word for word the same thing. And it also has an interesting geometric underpinning, or like a trivial geometric underpinning, if you prefer, by this basically just by Riemann Roch, because the analog of the different or of the codifferent is the canonical divisor or the canonical class if you go to the class group, and that the degree of that is always even. So it's a square, yeah. So that's if you work over the algebraic closure, but then a proof which is identical to the one we saw on the previous slide will also work if we do function fields over finite. Yes. Yeah, and so the theorem that we prove is you take this, if you accept this analogy, then the theorem says that this class is 0. Very much like the result we had for in the arithmetic situation. Yeah, so it's not clear at this point how this definition of different, if at all, interacts with the notion of spin structure that Arten talked about in his talk. Maybe because this is more of a relative notion for covering of branched covering of 3 manifolds, whereas Arten's the classical definition, if you like, is just an absolute thing where you take 1 manifold on 3 manifold and define define a spin structure on it. So it's not clear what's the relation between the notion. All right, so if you're happy with the statement, we can try to talk about the proof or the setup for the proof of this theorem. So we will try to basically do the first step will be identical to the one in the arithmetic situation. We will try to show that for all characters, once we apply the character to the element, we get 0. So that step is the same thing, and the characters of the first homology group, we can think about them as just cohomology classes. That's going to be. Yeah, so that's identical, so sort of. So that's just a different way to write the same thing. We just range over all the primes or over all the knots. Right. And so now we will try to use in some way, because we can't. So at this point, we have to diverge from the arithmetic proof, because there isn't such a nice local global kind of formula we can use, or at least I can see how to do this. But we will try to do something more geometric that's in the spirit of topology. So to alpha, we can associate, because it's a cohomology class, we can associate a double cover, like an honest cover, not branched anywhere. And then we can think of n. So n is a cover of m tilde, and m tilde via this map pi we're talking about is a cover of m. So we have a cover of a cover. So it's a degree 2 cover of a degree n cover. And as a result, the monodromy group of this composed cover is contained inside, or is a subgroup of the Reith product of Z mod 2 and Sm. And this is something called the hyperoctahedral group. It is very famous for some mathematicians, maybe not so famous. So one thing we get from this cover is the following sequence of maps, which will be useful later in the proof. So the first map here that I'm looking is because just it's a cover. So by functoriality of group cohomology, I get a map like this. Then of course I have a map from the cohomology of the group, the fundamental group, to the cohomology of the space. So the idea in the proof, one idea in the proof will be to take some cohomology class. This is already something within the realm of finite group cohomology, so it's a purely group theoretic thing, and get some interesting cohomology class on the manifold that will somehow relate it to what we actually want to do. So hold that thought, and I'm going to put you through at least 2 slides of group theory now. Let's do it. So I want to talk about this hyperoctahedral group in case you're not one of these people for which it's a famous thing. And somehow the bottom line will be to understand a certain class here. So I want to build a cohomology class, or in other words, an extension or a central extension of this hyperoctahedral group by Z mod 2. So that's kind of the kind of group theory I'm going to put you through in the next 2 slides. Yeah, so let's talk about this hyperoctahedral group and construct an extension of it. So I want to define a different group now in order to get to the extension. The group Hn is a direct product only set theoretically, but the binary operation is a little weird and is given by the following formula. So you can check that this formula it's associative, and that 0, 0 is a unit, and that the inverse is given by this formula. So you really get some finite group from this stuff. And this group turns out to be an extension of Z mod 2Z to the n just by the projection map by Z mod 2Z, some central extension, but not the not the trivial one. It's not like isomorphic to the direct product. It's not that, it's some other group.
I don't understand the doubling. Oh, okay.
There might have been a typo, possible, yeah.
It's a
Okay, never
semi-direct
mind.
product, so you could just tell us what the O2 is.
No, it's not semi-direct, because if you have a central extension, a semi-direct product would always be direct. Yeah, so that's not that. Yeah.
With some two codes.
Yeah, I'm really not torturing you with this formula for nothing. It's really the simplest one that I'm aware of. Yeah. Yeah. So one thing you can do, which is maybe nicer than this formula.
The 1 and the 2, the sum upstairs should disappear, right? Otherwise, I don't understand.
The 1 and the 2 are.
In the sum
Yeah.
line, there shouldn't be a 1 and a 2,
Well, I
right?
think there should. So A1I is accessing the coordinates of A1 and A2.
Oh,
So A1 and that's confusing
Oh.
notation. Yeah. So A1 and A2 are elements.
yeah,
of
yeah,
the-
yeah.
So they're vectors.
Right.
And I'm accessing the coordinates of the vector.
thank you.
Yeah, thanks for bringing it up, because this is confusing. Yeah, so another way maybe to describe this group which could be less or more mysterious depending on your perspective, is to write it as in terms of generators and relations. And the generators you take are these generators. So EI is the vector which is I at the 1 at the ith coordinate and 0 everywhere else. And then the other guy, the other generator I'm taking is like 0, 1. And it turns out that these n+1 elements generate this group Hn, and you can in fact write explicit relations. But yeah,
The operation is kind of like the Witt vectors, but like the dot product with the Witt vectors on the second.
it's yeah. So this I'm not writing the relations because that could be perhaps uglier than this formula. But what you can see from either description, hopefully, is that the group Sn, symmetric group, acts on the group Hn by permuting these generators and then by doing nothing on this other generator. So this guy which was in the center will remain in the center for this Sn action, and also after we take the semi-direct product. So that's what happens next. So that's the group that I wanted to construct. That's somehow the main point of the slide. You form this semi-direct product. And then because the action on 0, 1 was trivial always, this is going to be a central extension. That's basically what I say next. So when you mod out Gn by 0, 1, you get back the group Sn semi-direct product of Z mod 2Z to the n. So this is S2 read product Sn. That's the group. This is this hyperoctahedral group we're talking about. So eventually, because of this construction, Gn, what we constructed is a central extension of this S2 read Sn by Z mod 2Z. And we can view a central extension as a cohomology class in this cohomology group, which appeared in the previous slide. So that was the point of the slide, to construct a certain specific extension. And this gives us a very specific cohomology class, which will help us with the topology problem. But it's not enough just to construct the group and the class. We also need to know something about this group And this is what the next slide is going to be about, some basic group theory of Gn. So the thing we need to know about Gn is how, so what happens when you take the commutators of two elements which commute in the hyperoctahedral. When you take two elements in this hyperoctahedral group, two elements that you assume that they commute, and now you want to see whether they commute or not after you lift them. So that's basically what this phi or commutator is doing. It just checks whether they commute, just lifts and takes the commutator. If they commute, it's going to be 0 and 1 if they. And it turns out, because this is a central extension, and this will always be the case in a central extension, this definition is not going to depend on the choice of lifts. So you can just choose the lifts in an arbitrary way. Yeah, so the group theoretical problem kind of that we needed to solve is very simple and elementary, just to figure out what this one bit of information is for every sigma and tau that commute. And that's basically what I'm going to tell you. The slide, it's a very simple thing. So first you just need to notice a couple of things. First you notice that it does not depend on the order in which you plug sigma and tau. Pretty simple exercise. And then you check that the map, if you fix sigma, then the map which sends tau to this lifted commutator is a homomorphism in tau. It's just a simple computation. And then because sigma and tau, this does not depend on the order in which you plug sigma and tau. Then you can also show that it's a homomorphism also in the second variable. And then another simple computation you need to do to get the complete answer is to, maybe that's like the simplest computation, is to take sigma to be a cycle and to take tau to be a certain vector which is supported on precisely the same indices that appear in the cycle sigma. And then you just compute it as something simple, and you get that it's just the parity of k minus 1. That's the answer. And then from this information here, you can obtain the more complicated and complete formulas that we got for an arbitrary sigma and tau that commute by working from these cases and the general. So what we do is compute phi sigma tau for every sigma and tau that happen to commute in the group. Okay, so now let's try to piece these things together into a proof of the theorem. So let's just briefly recall what happened. So let's go a few slides back. So we constructed this cohomology class for the extension. This is beta n. And we had a map from group cohomology, where this beta n lies, into the cohomology of this manifold that came from the cover. And so now what we can do is to look at the image under this map of this element that we constructed. That's what I'm doing here. I'm denoting by some letter like gamma, the image of this class corresponding to the specific extension of the hyperoctahedral group under this map. Right, so what is the use of this gamma? That's, I guess, the question. So let's recall that what we need to show is the vanishing of the value of the character on this different in the class group mod 2 or in the first homology group with coefficients in Z mod 2Z. Now I will just put all these because I want to see if you see immediately the connection for why are we interested in gamma. So it turns out that and that's somehow the main point of why we need to do this group theory, or why is it useful. It turns out that the integral of gamma over a certain torus that you will see in a moment how it is defined, or maybe you already see, is precisely this inner sum. Yes, it turns out that using the integration of this cohomology class, you can access the thing that you want to show, the values that you want to show that sum to 0. That was the point of constructing this cohomology class and doing all this group theory, at least on the first slide. Now maybe now it makes sense to talk about what this torus T is. So what we do is basically, maybe the way to say it is, okay, the way I say it here is you take a tubular neighborhood of this link L, but it's basically related to taking the tubular neighborhoods of the knots which build up this link. And you denote by S the boundary of this tubular neighborhood, which is a union of tori. With tori, you will have one torus T for every component K, which is a knot of this link L. So the boundary of a tubular neighborhood of K is T. So that's basically what I said. And then it turns out that it's basically by so what you can show is that this integral that I'm talking about here over each such torus T is equal to this map phi from the previous slide applied to two specific elements which commute, and which two elements you need to choose a certain meridian and a longitude in your fundamental of the complement of the knot. And then by some further topological arguments that I do not want to put you through, you show that this phi, that this bit 0 or 1 phi ml is equal to the inner sum that you see here. And then to conclude, all you need to do is to note that there is this bijection between the components K of L and these components, the different T's, the components of S. So this big sum is just equal to the sum over these integrals. But then you can write this as an integral of gamma over S. But because S bounds a 3-manifold, so 3-manifold inside the complement, then you necessarily get that this is 0. Yeah, I think that's basically. Okay, yeah, I stopped.
Thank you. Other questions?
Yeah, questions from there.
Is it easy to say what the class in H2 of RP infinity to the n is that gives you your group HN?
Yeah, that's a good question. Yeah, I think it's written in the literature, but off the top of my head, I won't remember this right now. But I think this should be known. Yeah.
It's not like something, it shouldn't be obvious to me what it is.
Yeah, I would need to think about this. Yeah. It's just that it's a good question, but for the purpose of that argument, I'm not sure it would have been helpful for us to know that. So we didn't get into it, but I think, yeah, I think that this might be somewhere written down. Yeah, I'll have to think about it. Yeah, good question. Magnus, you had a question?
So if I'm in the number field setting and if I have a tamely ramified extension, can one translate your topological proof to get like a proof of the number theoretical thing?
Yeah, yeah, I was also thinking about it, but it wasn't completely obvious to me how to do this. But I still want to believe that there is some way. Yeah, it's not wholly evident.
Yeah, but it looks very similar, so it's
Right. Yeah.
But there was a heart in number theoretic proof, right? That equality between epsilon factor and a valuation of the different.
Right.
I mean, is there an analog in this proof, like topological setting? Somehow Gauss sum and integral.
Yeah. So in this proof, I don't see this analogy, but this is a very good question because there is another proof of this result that was communicated to us by the referee of the paper. And that's, by the way, the best way to reject the paper, if you can give it as a proof. So the referee gave a proof in the case under the assumption that the manifolds are orientable. And he uses triangulations and he uses the simplicial approximation theorem. And so it seems to me that in the proof of the referee, that is more similar to the proof in the even though it's still, yeah, so of course some of the ingredients there are also not arithmetic, but it feels to me that that proof is more reminiscent of the arithmetic argument than this proof is. Yeah,
Could
question.
you say again what the phi ML is and maybe a bit more about what the extra topological?
No, I mean it's just piecing the things together, so it's not. Yeah, I want so that part. If you are interested, I really want to refer you to the paper.
Okay.
It will really be great if, as a result of the talk, someone will take a look at the paper. Apart from the referee. So yeah, so phi is just the thing that measured whether
Okay.
these things
And
not
MLN are the meridian.
gradient and longitude. Yeah, the fun.
So for that, you have to fix some sort of framing for these knots.
No, we don't need to do it. Yeah.
How do you specify what M and L are?
I think that this will work for any choice of M and L. I think so. I think for every,
Mental group is, you just take any two generators.
I think it works for, yeah, that
Two
part.
generators.
More questions? Yeah.
Is the gamma supposed to be like the analog of the relative spin structure that?
It's a good question. It's hard for me to say, because I think that yeah, so probably the spin structure, right? It should either lie, I guess, in H1.
Yeah.
Or what, or even like the spin structure over
I mean, it's not actually a spin, but I mean, some
Yeah.
extension you need so that you can make this.
yeah, it's hard to say because like over number fields, right? The spin structure, you can either think of it, I guess, as an ideal or an ideal class, maybe, yeah? And the analog of that, like naively should be H1. But maybe there is something that this class gamma, like maybe if you like apply Poincare duality or something like that, maybe you can relate it to something in H1. Maybe an idea, but yeah, perhaps I should think about it.
Kind of common question.
Yeah.
Previous question. I think this kind of is some version of class field theory in the three manifold setting because you're converting alpha as a character
Sure.
between that and a double couple.
Oh yeah, absolutely.
That's like, yeah, it's like class field theory, and then this gamma sits in H2, so it's kind of like Nakayama or the fundamental class. And exactly copying with that is what converse between.
Yeah.
Yeah.
Yeah, that's fair. Yeah.
This is like local integral, in two ways, using Galois side.
Yes. Yes, that's right. Yeah. Yeah, I completely agree with that. Yeah, that's a very good point. But maybe what is missing in this picture is somehow the local to global, like in classical theory, one of the things that is also kind of visible in in the original, in the proof of the arithmetic case is that you factor something into information, one bit of information for every place. I don't feel like there is something like that in this proof.
Isn't that the separating into components? And then in the end, you use Stokes' theorem, right? So that's like knowing that the global sign is one.
Yes, it is, but, but somehow, so somehow you only took. Yes, that's a fair point, absolutely.
So, in that last equation, it looks like the right-hand side depends on alpha, but I don't see how the left-hand side depends on alpha. Is it?
It doesn't, yeah, I mean, eventually.
Doesn't, okay, yeah.
Eventually, the goal is to show that this thing is equal to zero, which
Okay,
is
so
also-
you're showing the individual parts are individually independent of alpha, right? But is that also what was going on in the other proof for the number theoretic analog for Hecke's theorem?
Yeah, because you want every character to kill.
Yes.
Yeah,
Yes.
right, so eventually it's something, yeah, which is independent of it.
Right, yeah.
Okay, more questions?
No more questions. Let's thank Mark. And dinner is at 6. St. Leonard Wood.
What time are we leaving here?
So we've, I don't know. I don't know the address yet.
But not in a way that's helpful to you.
Yeah, that's a very good point.
So like the vanishing of like the local and like the local and like the